I'd like to take a look at deriving power series expansions from known power series expansions. At the top of the page, we have the Maclaurin series, the Taylor series around x equals 0 for three common functions. The first is e to the x, and that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And that converges on the entire real line. The second is the Maclaurin expansion for sine x, which is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on, alternating positive and negative terms. And that converges also on the entire real line. And the last one is the power series expansion for 1 over 1 minus x, which is just 1 plus x squared plus x cubed plus x to the fourth, and so on. And that one converges on the open interval -1 through 1. Taking those as given, and again, I should emphasize that we need to commit those to memory, let's take a look at the Maclaurin series for cosine of x. We observe that cosine of x is nothing more than the derivative of sine of x. And we know the power series expansion for sine of x around x equals 0. So this is the derivative of x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh plus, and so on, alternating plus and minus, plus and minus. And we'll take it for granted that on the interval of convergence we can differentiate this term by term. So the derivative of x, of course, is 1. The derivative of the next term, the 3 comes down and cancels out the 3 in the denominator, leaving us with 1 over 2 factorial. 3 becomes a 2 using the power rule. And the next term, the 5 comes down. We end up with 1 over 4 factorial x to the fourth. The next term, the 7 comes down. 1 over 6 factorial x to the sixth. The next term would be plus, and so on. So we have the Maclaurin series expansion for cosine of x, which comes up so often that I highly recommend committing that one to memory too. Now let's take a look at the Maclaurin series for cosine of 2x. We already, fortunately, have the Maclaurin series expansion for cosine of x. We just want to put a 2x in wherever we have an x over here. So we have 1 minus 1 over 2 factorial 2x all squared plus 1 over 4 factorial 2x to the fourth power minus 1 over 6 factorial 2x to the sixth power. The next term will be plus, and we can clean this up a little bit. So we have 1 minus 2 squared all over 2 factorial x squared plus 2 to the fourth power, the 2 is raised to the fourth power, over 4 factorial x to the fourth minus 2 to the sixth power over 6 factorial x to the sixth, and so on. Again, we are going to ignore the important questions of convergence, and we're also going to take a somewhat blasé attitude towards integration and differentiation. Let's take a look at sine squared of x. In order to write the Maclaurin series expansion of that in terms of functions that we already have, we're going to remember the double angle formula, which was the same thing that allowed us to integrate this, find the antiderivative of sine squared of x. So we know that sine squared of x is equal to 1 minus cosine of 2x all over 2. And we can break this up into two fractions. This is 1/2 minus 1/2 cosine of 2x. And fortunately, we have the Maclaurin series expansion of cosine of 2x immediately above. So we have 1/2 minus 1/2, and then we will rewrite this Maclaurin series expansion. 1 minus 2 squared all over 2 factorial x squared plus 2 to the 4th over 4 factorial x to the 4th minus 2 to the 6th over 6 factorial x to the 6th, and so on, plus and minus. And now we can do a little bit of simplification here. We have 1/2 minus 1/2 times 1. The constant term cancels out. That minus sign, of course, distributes into the rest of these terms, and we're going to multiply each term by the 1/2 in addition. So minus times minus, the x squared term becomes plus. We have 2 to the 1 on top and our 2 factorial on the bottom. X squared, again, that 2 to the 1 because the 2 down here cancels with one of the 2's in the numerator. The next term is going to have a negative coefficient. Minus times plus is minus. That 2 cancels out with one of the 2's in the numerator, making it 2 cubed over 4 factorial x to the 4th. The next term is going to be minus, have a negative coefficient, 2 to the 5th over 6 factorial x to the 6th. That one should be plus. The next one will be minus, and they keep alternating plus and minus. Let's go on to e to the x squared. This function, of course, when one studying integration in terms of elementary functions, is quite interesting because e to the x squared cannot be integrated in elementary terms. But we can go ahead and write its Maclaurin series quite easily. Basically, we're just going to take the Maclaurin series for e to the x and plug in an x squared where we see an x. So we have 1 plus x squared plus 1 over 2 factorial x squared squared plus 1 over 3 factorial x squared cubed, and so on. And we can clean this up a little bit. 1 plus x squared plus 1 over 2 factorial x to the 4th plus 1 over 3 factorial x to the 6th, and so on. And of course, if one wanted to integrate this Maclaurin series expansion, one could certainly do so term by term. Now let's take a look at e to the x plus e to the minus x. For those of you that are familiar with the hyperbolic functions, you'll recognize this as twice the hyperbolic cosine. So we're going to write the Maclaurin series expansion of e to the x exactly as it is. 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus, we'll put one more term in here, x to the 4th over 4 factorial plus, and so on. And now we're going to add the Maclaurin series expansion of e to the minus x, basically just plugging in a minus x wherever we see an x over here. So in the interest of saving time, I'm going to do a little bit of algebra. So 1 plus, we'll put a minus x in there. So that would be, that would be minus x. And the next term, we're going to have 1 over 2 factorial minus x all squared. The minus signs cancel out. So plus 1 over 2 factorial x squared. The next term is going to have 3 minus signs in it, so minus 1 over 3 factorial x cubed. The next term is going to have 4 minus signs. They all cancel out. So plus 1 over 4 factorial x to the 4th. And continuing, minus plus minus plus. Now we just go ahead and collect up like terms. So 1 plus 1 is 2. And then the x and the minus x cancel out. We have a 1 over 2 factorial x squared plus 1 over 2 factorial x squared. That's 2 over 2 factorial x squared. The x cubed terms cancel out, minus 1 over 3 factorial plus 1 over 3 factorial x cubed. But we have an x to the 4th term, so 2 over 4 factorial x to the 4th. When we take this and add it to that, the next term is going to be a plus 2 over 6 factorial x to the 6th, and so on, every term being positive. Let's continue now with 1 over 1 plus x, which is the same thing as 1 over 1 minus negative x, allowing us to use our expansion of 1 over 1 minus x, plugging in a negative x everywhere we see an x. So we will have a 1 plus negative x plus negative x all squared plus negative x all cubed plus, I'll put in one more term, negative x to the 4th power. Oops, have these powers in the wrong spot. 3 to the 4 plus and so on. And when we put this all in, we end up with 1 minus x. The minus signs cancel out, plus x squared. We have 3 minus signs here, minus x cubed. We have 4 minus signs, plus x to the 4th. And it continues minus plus forever. Now let's take a look at the natural log of 1 plus x. We recognize right away that the derivative of the natural log of 1 plus x, we can use the chain rule on that. That's 1 over 1 plus x times 1. So the derivative of the natural log is this. We already have the expansion of 1 over 1 plus x. That's equal to 1 minus x plus x squared, plus x squared minus x cubed plus x to the 4th, and so on. So the derivative of the function that we want is this function, and we know the Maclaurin series expansion of that function. So if we want the Maclaurin series of the original function prior to taking the derivative, we just want to take the antiderivative of this Maclaurin series expansion. So the antiderivative of 1, of course, is x, and the antiderivative of x minus x is going to be minus 1 over 2 x squared. The antiderivative of x squared is going to be 1 over 3 x cubed minus 1 over 4 x to the 4th plus 1 over 5 x to the 5th minus, and the only thing that could possibly have gone wrong here is that we have the constant incorrect, but we have, if we take a look at the natural log of 1 plus 0, we see we get the natural log of 1, that's in fact 0. And if we plug in 0 to the right side, we see that these two equal, so that works out very nicely. Now let's take a look at 1 over 1 plus x squared. So we already have the expansion of 1 over 1 plus x. Let's go ahead and just put an x squared in everywhere we see an x. So this is equal to 1 minus x squared plus x squared squared minus x squared cubed plus x squared to the 4th power, and so on, plus and minus, minus and plus, and we're left with 1 minus x squared plus x to the 4th power minus x to the 6th power plus x to the 8th power, and continuing plus minus plus minus. Now we'll take a look at the expansion of arctangent of x. We'll recall that the derivative of arctan of x is equal to 1 over 1 plus x squared. And we already have the expansion of 1 over 1 plus x squared, which is equal to 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus, and so on, alternating in sign. And we're going to use the same trick that we did up here. We have the Maclaurin series expansion of the derivative of the function that we want. So now we're just going to go ahead and take the antiderivative. And if we antidifferentiate 1, we end up with x. If we antidifferentiate x squared, we end up with minus 1 over 3 x cubed. If we antidifferentiate x to the fourth, we have plus 1 over 5 x to the fifth. If we antidifferentiate x to the sixth, we have the minus 1 over 7 x to the seventh. The next term is going to be plus 1 over 9 x to the ninth. Next term is going to have a negative coefficient. And again, we can see that arctan of 0 is 0, and if we plug 0 into the right side, we have 0, so our constants work out okay. One last one. Let's take a look at 1 plus x over 1 minus x. We'll write this as two fractions. We'll write this as 1 over 1 minus x, and we will add it to x over 1 minus x. That's the same thing as writing 1 over 1 minus x plus x times 1 over 1 minus x. The expansion of 1 over 1 minus x is 1 plus x squared plus x cubed plus x to the fourth plus and so on, plus x times the same expansion. So 1 plus x squared plus x cubed plus x to the fourth plus and so on. And we're going to go ahead and multiply that x in. So we have 1 plus x squared plus x cubed plus x to the fourth and so on, plus x times 1 is x times x is x squared, x times x squared is x cubed, plus x to the fourth, plus x to the fifth, plus and so on. And now it's just a matter of adding up like terms. We have a 1, we have an x and another x, so plus 2x. We have an x squared and another x squared, 2x squared, 2x cubed, 2x to the fourth power, and so on forever. And that is the technique.